Hello? Okay. Okay, cool. You ready? Okay. Hi. Thanks everyone for coming. We have a wonderful session on reinforcement learning. Hope everyone's excited, at least for the air conditioning. First, we'll have Max tell us about the pitfalls of imitation learning. Take it away.
Hi, everyone. I guess I've got to bend down for this. Thanks all for coming and for braving the heat. So I've seen that there's been a lot of excitement, obviously, in this session, in this conference around language models, and rightly so. Their capabilities are quite impressive. And maybe a very natural abstraction for pre-training language models might be something like imitation, right? So we could imagine that we use natural human language as a form of demonstration data from which we try to predict subsequent tokens, as if imitating an expert which produced that language. But I actually spend a lot of my time thinking about the continuous world. So we can think about the same paradigm being applied, for example, in robotic behavior models, where now rather than having language that's available on the internet as our form of demonstration, we instead consider the possibility of having human demonstrators collect data, say via teleoperation, for robots that might use that data for some form of activity down the line. So in this setting, the goal is to predict, say, a next action given an observation, maybe pixels, tactile sensing, etc. And I think there's a very fundamental question that one can answer, right? So if we, or try to ask, if we look at something like GPT, for example, this is something that's predicting discrete tokens, right? We've got tokenization of our language, and yet on the other hand, robotics, we're predicting continuous actions. So we might ask ourselves, is there a fundamental difference between this discrete versus this continuous kind of decision-making that we encounter? Okay. So what we'll do is we'll study this from the perspective of imitation learning. We'll formalize it as follows. So I'm going to use X for states and U for actions that's following control conventions. Dynamics are going to be deterministic functions of state and input. A policy is going to be a mapping from a state to distributions over inputs. And finally, we'll have some cost function. And the cost will be bounded and Lipschitz. So what is our goal? Well, our goal is to have low excess cost relative to an expert. So here, expectation under pi hat is going to denote expectation under a learned policy pi hat, denoted in red. Expectation under pi star is going to denote expectation under rolling out the expert policy, which we're trying to imitate. And we're going to look at cumulative cost under both of these, right? So just cost under imitator excess over cost over expert, excess risk. And we'll do this over a horizon or number of problem steps H. So how do we do this? We accomplish this just by collecting a sample of trajectories which are drawn from the expert distribution from which we need to imitate. So just to get some intuition for what you might do to minimize this cost, one very reasonable proposal is to do something called behavior cloning. The results in this paper apply far beyond that, but what you can do is you can try to specify some loss function that measures how close your learner policy is imitating the expert data. Right? So you have pairs of actions and inputs from the expert data. So you can try to use a square loss if you'd like. You can try to use a 0-1 loss, which would work if you're discrete. You can use a log loss. There's been some really wonderful recent work on that. And actually, oftentimes, we might even use things like diffusion or flow matching as ways to predict conditional distributions. So these things are very popular in robotics as well. Now, it's important then, if we think of behavior cloning as a natural algorithm, to think of the baseline, which is to compare how well we do in terms of this excess error to some notion of supervised learning risk under the distribution of expert data. So we'll call this R expert, which is specified by a loss function. And it just says how much loss do we incur if we consider drawing states from expert data. And this should be an X star, not a pi star, sorry. Right, and this can be minimized by pure supervised learning relative to our loss function. Okay, so why is imitation a hard problem? It's really this issue of compounding error, right? So imagine that we have our notion of expert, right? This is sort of the error, the thing under which we have low error. And what this sort of specifies is that if I go along in any expert trajectory, the actions that I would predict from my own policy would be somewhat close to what the expert would do. But of course, that's not what imitation learning actually asks of us. What imitation learning wants us to do is deploy a learned policy. And as we do the deployment, the errors can accumulate over time steps, becoming larger as the horizon grows. And perhaps more perniciously, as these errors accumulate, so too can we arise out of distribution from our training data and not know quite what to do. So with that said, what is known about the compounding error problem? So there's actually a folk theorem which says that if you're able to minimize the 0-1 loss, and if your costs are bounded in 0-1, then sort of for all pairs of policies pi and pi star, agnostic of the algorithm that you use, your imitation learning cost is going to be bounded by your horizon times the expert cost. And the way to think of this is just a simple union bound or telescoping sum. You can just make at most one error at every time step, and these accumulate linearly. And there's some really beautiful improvements due to Dylan and Adam and others using the log loss, which hold in certain situations. And this tells us maybe very nicely, okay, compounding error is at most linearish in the horizon in an algorithmic independent way, which is nice. But here's the problem. This requires a 0-1 loss, or things that might be even stronger like KL or chi-squared. And we know that we can't do many kinds of statistical problems to non-trivial error in the 0-1 loss. For example, non-parametric estimation will inevitably have some residual metric error that we'll make. So unfortunately, these bounds are going to be vacuous in this setting. So the question we wanted to answer in this paper is what actually happens in a continuous state space. So I'm going to state the theorem. Pick your favorite number. Think of this as like an exponent of decay. And what we can show is that there exists a family of nice imitation learning problems in dimension as small as 3, such that given n example trajectories, you can learn them in a very natural loss. So you can learn them, for example, in an average L1 loss decaying as n to the minus k. So this is your k is your chosen rate. And again, unlike the 0-1 loss for, say, general non-parametric families, this is a thing that is actually attainable, right? Actually attainable. Now, on the other hand, if we consider the imitation loss, there exists a 1 Lipschitz bounded cost. This is a cost that's known to the learner, and it's bounded, so it's not blowing up to arbitrary large magnitudes. But any learning algorithm which returns a proper policy necessarily suffers the same rate of estimation times 2 to the h. Of course, minimized with 1 because our cost is bounded. Right? So stated otherwise, we have a deployment error that can be exponentially larger than the expert distribution error in this continuous setting. I should also mention that the system that we consider in the lower bound is intentionally chosen to be very non-pathological. The system satisfies a control theoretic property called stability, which roughly means that it's relatively insensitive to inputs to the system. The system is also smooth. It can be made to be C infinity if you'd like, and has a lot of other really nice properties like controllability. So this is not just that the dynamics are pathological. The second thing is that the round is agnostic to the choice of algorithm. It applies both to behavior cloning as well as to algorithms like offline reinforcement learning that might be aware of the cost. Because again, in this game theoretic formulation, the cost is given to the learner beforehand. Okay. And finally, the lower bound actually can be broken, and it can be broken by many clever tricks that actually resemble what practitioners do. And so in some follow-up work, we're actually demonstrating the power of some of these tricks to kind of circumvent the lower bound. And finally, I should mention that if we're allowed to make the system somewhat more pathological, in fact, we can make this lower bound unbreakable. So this bound holds truly for any algorithm, right? Not just proper learners. So maybe in the remaining time, I just want to kind of give a sketch about why this might hold. And the first step is actually to kind of come up with a very simple counterexample from linear dynamical systems. So a linear dynamical system, this is just a system where the dynamics function is constrained to be linear. We'll take it to be this form in the blue. And we'll also consider linear control policies, which can be also represented linearly as follows. And essentially, we're able to show a very simple dichotomy, where we have these two linear systems that agree on one subspace, E2, and if any other controller is to agree with the data on that same subspace, then there will be one system that it actually has to destabilize. By destabilizing, we mean making sort of exponentially sensitive to small errors, whereas the other system might be stabilized. So there's now a tension between agreeing with the expert demonstration data, which one has to do for small imitation learning error, and ensuring that the closed-loop behavior of the system and the controller is well behaved. Now, what we can do is we can carefully embed a non-parametric learning problem into this example, and kind of use that non-parametric learning problem as a source of initial error, which via some bump function tricks essentially gets carried through in the linear system, becoming amplified. And maybe the kind of core conceptual takeaway here is that what's going on is we have some metric notion of error, which is something that doesn't really arise in these more discrete settings. And hence, we pay for more than this union bound. We can actually pay for some exponential accumulation. Maybe just to conclude before the questions, continuous action spaces can be far more precarious than we encounter in language. And I think it requires substantially rethinking some of the formalisms that we bring to some of the RL reinforcement literature. So if we kind of investigate some of the setup of this problem, we find certain assumptions that we might like to make, for example, Lipschitz of Q functions or other assumptions, they really fail to hold, even in very benign, smooth, and stable dynamical systems. And so I think if we think about continuous action spaces, it's really kind of important to start with what makes sense for natural models of the dynamics, and then work our way backwards to other quantities that we might typically have taken to be kind of axiomatic in kind of more conventional RL theory. So with that, I'm happy to take some questions. Adam.
Great, thanks for the great talk. I guess my one question is, when you talk about...
Adam, you can come up here and just use the mic.
Okay, thanks for the great talk. One question I had is, when you're talking about the lower bounds against the improper algorithms, I guess there have been a number of empirical papers that discretize the continuous space and then just do kind of discrete behavior cloning on that. And while maybe this won't work in high dimensions, would this not break your lower bound in the kind of 3 dimensions because you're only paying kind of quadratically there?
We've tried
cubically.
So we've tried to do this. We've tried to do this. So there's two notions of there's two places where the discretization can take effect. So the discretization can either take effect at the initial non-parametric error. That will not fix the lower bound. Now there's like another question of whether or not you can use discretization of this system over here, of the part where the sort of instability arises. Yes?
I guess I was wondering, it seems like the main step. It seems like the main step here is showing that you cannot hope for an analog of the reduction of regret to Hellinger error between the
Correct.
induced rollout distributions, Correct. Right? So suppose that we treat the non-parametric estimation problem as kind of solved by the transformers, right? Then your lower bound is saying that any proper algorithm can't have this kind of comparison. Is that what I'm saying?
Yes, that's correct. I guess the question is what I'm trying to understand your question is where would you use the discretization to break the lower bound? So you can try to use the discretization for example, try to use a transformer to do this, or maybe say this in a different way. If you try to use discretization, you'll decompose into some sort of probabilistic, say, Hellinger error, and then a discretization error epsilon. And essentially what the lower bound is saying is that error epsilon will be compounded through the system, provided you have some conditions on what your learner does. Now, there might be some ways to get around it with smart projections onto a discrete set, but it seems actually quite non-trivial. And we can talk about it offline, but there's some technicalities as to whether this works. I should also mention that the kind of the policy class we're considering is smooth anyway. So to be proper, discretization sort of violates properness.
Oh yeah, you said that you also had some results for improper.
Oh, for improper, this is going to, so this is in an unstable dynamical system. In that situation, the discretization error will compound no matter what. Essentially, that construction, I can tell you offline. You have to use random orthogonal matrices and stuff.
One super quick question.
The question is, okay, let's try.
I'll just see how fast I can answer it, yeah.
So this is a 7-part question, no, kidding. If I understand correctly, this is only, the lower bounds is only if you insist on minimizing this
No,
action?
it's algorithm agnostic. It holds for any proper algorithm. So really, the form of the lower bound says there exists an algorithm which, here, let me write it this way. There exists algorithms which can attain this, but no algorithm can attain this.
I see.
It's
So
not just that if you minimize this, you have to be small. It's truly that no algorithm can attain this that's proper. Yeah, we were careful to make sure that was the case.
Yeah, let's thank Max again for the wonderful talk.
Thank you.
You ready?
This is the.
Sorry. Apologies again for technical difficulties. Wait, what's happening?
Does it need to be like this is not there?
Can you do just full screen? Yeah. C'est toi. Je ne vois pas. Attends, je cherche. Ah oui, présente, excuse-moi. Pas de problème.
Yeah, for the next talk, we'll have Matthew telling us about average reward RL.
Yep, thanks. Yeah, so hi, I'm Matthew, and I'm presenting this paper, which is joint work with my advisor, Yudong, and we're both from Wisconsin. So yeah, this paper overall studies average reward reinforcement learning, which is like the right criterion when you care about long-term performance in a continuing setting. And in particular in this paper, we study the sample complexity of learning near optimal average reward policies. So the main contribution of this paper is that we provide the first statistically optimal algorithm in terms of this optimal bias span parameter that I'll introduce later, which is prior knowledge free. So this is for two settings I'll define later. And this is the result of a new algorithm which performs a certain data-driven parameter tuning procedure. And then we also showed that it's possible to go beyond minimax optimality for the sample complexity of average reward MDPs. We show a new guarantee, which we describe as an oracle inequality guarantee, where we can compete with the policy that has the best sort of trade-off between complexity and suboptimality in ways that I'll make precise later, with using a new algorithm. So I guess, yeah, I'll assume that we're all sort of familiar with this, so we're just considering the tabular MDP case, and I'm using MDP, standard RL style notation with S and A, and yeah, I'll use pi to denote policies. So I guess, yeah, the standard discounted objective that we're all familiar with is the discounted value function, which I'll denote v gamma pi, and the optimal value function with a star. And so in the average reward setting, right, what the objective is the gain of a policy pi. So this is this quantity rho pi of S, where S is the starting state. So right, what this quantity is we look at the rewards, the expected rewards, cumulative rewards over a horizon of t, and then take the average, so divide by t, and then take the limit as the horizon t goes to infinity, or you can also write it in this other way if you prefer writing it with discounted value functions. And the optimal gain is similarly, you can take the supremum over this over all policies. And so the two settings that we'll consider, so the first is this batch data set setting or fixed n setting, where we have a fixed data set with uniform coverage. So just for every state action pair, we have n samples from the next state action transition distribution. And the goal is just to learn the best possible policy with our fixed data set. The other setting is more similar to this PAC-RL setting. So the algorithm is given an input epsilon, and so this is the target suboptimality, and with high probability we must return an epsilon optimal policy pi. And we can continuously sample from the generative model, possibly adaptively, until we do so. So while this setting is often harder than the previous one due to the need to upper bound the suboptimality, it also involves a stronger access model in general. So there is very recently an algorithm which achieves the optimal sample complexity or optimal minimax rate for both of these settings. And this algorithm uses reduction to a discounted problem, so approximates the average reward problem by a discounted problem. And unfortunately, it uses knowledge of this complexity parameter h, which is the optimal bias band. I'll define it in one more slide. But basically, this algorithm is unimplementable. It's not possible to estimate this h parameter, and we need to know it exactly well enough to run this algorithm. So while it's statistically optimal, it's not actually implementable. And then there's been a flurry of recent research trying to actually obtain implementable algorithms. However, all the implementable algorithms have had worse complexity parameters and/or worse scaling. For some of these settings, or one or both of these settings. And so it's been shown, like I just said, that estimating this parameter is impossible, so it's not easy to easily make this optimal algorithm implementable. And also some very natural approaches to removing prior knowledge are provably suboptimal, provably fail to obtain these optimal rates or sample complexities. So we resolve this problem in this paper. So we present a new algorithm, which we title horizon calibration. It's a method for calibrating this effective horizon that matches these statistically optimal rates and is actually implementable. So I'm just really quickly going to like flash the definition of H, the optimal bias span parameter in front of you, and it doesn't matter if it doesn't stick. So I guess like a one-word or one-sentence intuition for what this parameter is measuring is the maximum over all pairs of states, maximum deviation in cumulative reward from the long-term average. So just like the key things I want you to take away or know about this is that it captures the reward structure, whereas many other complexity parameters only measure like notions of time. It's always finite, whereas many other parameters are unbounded or undefinable, even for very like simple, nice MDPs. And most interesting from a learning theoretic perspective is that if we can obtain a bound that's based on H, that means that we can learn with a complexity that depends only on properties of the optimal hypothesis. So like this definition here only depends on like the optimal policy or some notion of optimal policy, as opposed to like arbitrarily suboptimal policies. So the optimal algorithm, which is statistically optimal but unimplementable, is very simple. It just does the following. So we can take our data set, I guess for the fixed data set setting, just construct an empirical MDP based on empirical transition counts, set the effective horizon in this like very specific way, which depends on this H parameter, and then we just return the policy which is optimal for this empirical discounted MDP. So it's a discounted plug-in approach. Right, like why does this work? Like what does setting the effective horizon in this specific way, what does it do? So we can think of it as controlling certain approximation and statistical errors. So by approximation error, I mean the error due to approximating an average reward problem, right, which is what we actually care about, with a discounted problem. And then statistical error due to like the suboptimality in solving this discounted problem that we've defined from samples. And so it doesn't matter like what these terms are. So both of them involve, like the key thing here is that both of them involve this H parameter, and so it's not easily possible to balance them from data. And yeah, so you can see like one of them gets smaller, the approximation error gets smaller as you increase the effective horizon, the statistical error gets larger as you increase the effective horizon. So like we want to balance them. And so a key underlying result with our first main theorem is that it's possible to get refined bounds on both of these terms in some sense, which are actually estimable. And so that leads to like this following lemma, where basically it looks the same as the lemma I just showed you, but we've replaced this H quantity with this new quantity, which is the span of the empirical optimal discounted value function. So like a subtle thing here is that this depends on gamma. This depends on like the gamma that we're trying. But so this quantity is actually something that we can like try to get a handle on from data and try to control both these terms at the same time. So that motivates our algorithm, right? This expression here, which if you look at the left-hand side here, so we have like this whole expression is like a confidence interval for the suboptimality of our policy. So now we can perform data-driven tuning of gamma by just trying a geometric grid of effective horizons and then optimizing this error bound. Right, we just estimate the transition kernel same as before, try this grid, and return the policy, which minimizes this confidence interval. And so this is the result, this is just saying, yeah, it gets the minimax rate for this like fixed data set setting. It can also be used to estimate the optimal gain in a rate optimal manner without prior knowledge. And then for this fixed epsilon setting, actually all the key ideas are already there, and what we can just do is keep doubling our data set size until we finally get one of these confidence intervals to be smaller than epsilon. So lastly, I'll just first show you sort of what's possible in terms of going beyond minimax optimality for the setting. So this is just for the fixed n setting. And so we develop a new algorithm called empirical span penalization, which has the following guarantee. So it returns a policy pi hat satisfying the following. So on the left-hand side here, we have the gain of the policy that we return. And on the right-hand side, we see it competes with like a supremum over all policies. So it's sort of optimizing a certain trade-off. And looking at these two terms, so right, we have the gain of a policy, of a comparator policy pi. And then the other term is like the complexity just to evaluate the gain of that policy pi. So yeah, we call this guarantee an oracle inequality guarantee because it means that we automatically compete with whatever policy pi has the best trade-off between suboptimality and complexity. So like we can easily recover the minimax rate just by setting pi to be like an optimal policy, but it's potentially much better if, for example, we have policies that are slightly suboptimal but very simple. So I'll quickly give some high-level ideas for this algorithm. So I think if I told you this theorem is possible, maybe the most natural idea is to try this empirical, to try the penalization approach. So to try to solve an optimization problem that looks like the following. So this left term is just a gain estimate, and then we subtract some penalty terms such that this overall expression is a lower bound on the policy that we're returning, and we try to maximize this over pi and also gamma, which sort of controls the error bounds, the penalty terms. And so while this is itself not clear how to implement, we can introduce a superfluous constraint, a span constraint, in terms of this parameter. The span constraint is m, and we can also optimize over this m parameter. And then we get this equivalent problem where, crucially, we've removed the dependence on pi in a lot of these terms. So the terms that depend on pi are just this one term now, where we have this span-constrained planning subproblem, and then the rest of the terms are just scalars that we can deal with separately. So the span-constrained planning subproblem, it could actually be infeasible, but there's a certain relaxation of it, which is possible to sufficient to get this whole thing to work, related to an idea by Rodent Fruit. And so it ends up being that we only need to coarsely optimize over the span constraint, and that gives us an efficient algorithm that achieves the theorem I just told you about. So yeah, here's my main contribution slide again, and yeah, that's all. Thanks for listening.
Oh, we have time for quick questions, and I think Ankur has one.
Oh, sorry. Did you define the span constraint? Maybe I missed it.
Sorry, yeah, I did. I flashed it in front of you, but I did not. So, yeah, sorry about that. So the span is the maximum entry. So I guess, yeah, this expression here is for any vector. So it's the maximum minus the minimum entry.
Okay, so maybe but here you told us that the h parameter wasn't estimable, right?
Yeah.
But then the relaxation you had, did you tell us how that is defined or how it's estimable? Maybe I missed that part.
Yeah, so this h parameter is a property of the, sorry, let me think about your question. So, I mean, this h parameter is a property of the true MDP, and so it's not possible to estimate this parameter from data. However, so yeah, this relaxation here is in terms of a quantity related to the empirical MDP. So this is a value function. This v hat gamma pi is a discounted value function for the empirical MDP. So we could always compute this value function, even if we're an average ordered relative value function as opposed to a discounted function. We could always compute this for the empirical.
And
MDP.
sorry, the SP of that is just its span.
Yeah.
Okay.
Sorry. Yeah.
Yeah. Gotcha.
Let's thank the speaker again, and yeah, we'll next have Jean giving us a talk about the role of environment access in agnostic RL. Jean, take it away.
So today I'm going to talk about this paper, which is joint work with Akshay and Ayush, and both of them are here, so please also catch them if you have any questions. I guess it's, I don't really need to say this, but RL and interactive decision making has made a lot of strides empirically. So from game playing, autonomous driving, healthcare, control tests, as well as even training LLMs. And so a common characteristic of all these problems is that they involve, they're sequential and they involve a huge state space. And as such, it's really natural to ask how much data do we actually need and what sort of algorithms should we use. In this talk, I'll mostly focus on the finite horizon MDP. And just to briefly just run over the notation, I'll use X for state space, A for action space, and then we'll have an initial state distribution and probably transitions, rewards, and H is our horizon. So the most common interaction protocol is this sort of like online interaction where the learner can basically get trajectories from this MDP. So they get an initial state, and then for H rounds, they propose actions and then observe the next state and reward. So what is the goal? So the goal really is for the learner to find some policy, which is a mapping from states to actions, that maximizes like the cumulative reward over these H steps. And to help out the learner, we're going to give them access to like a policy class. So this is like a set of policies that represents our belief of like what a good, a high value policy might be. You can think of this as like neural networks of a fixed architecture. And we're also going to give them access to like some kind of interaction protocol. So I've already talked about this online interaction, but of course there are many others. And like the goal here is like this pack objective, which is we want to output some policy, pi hat, which competes with the best one in the class. And this is like what we'll call an agnostic pack learning guarantee. And so, of course, without any sort of assumptions, this problem is statistically intractable. So what if people try to do? So I guess there are two sort of categories of structure that people have tried to make. So one is this like notion of coverage, which kind of measures how much exploration we need to do in the problem. And the other one is like representation, which is that if we have some kind of function approximation, maybe we have a value function approximation, what sort of functions can be represented by our function class. And in this work, we're going to like study this third kind of structure, which is the interaction protocol. And we're going to study like how they interact with these other two sorts of structure. To give you one sort of example, there was this recent work by Mérieux, Foster, and Rockland, which showed that for value-based RL, if you have like local resets, meaning that the learner can reset to states that they've already seen, this allows us to relax this like Bellman completeness assumption, which is like a very strong representational assumption on the function class. Okay. But of course, in this paper, we're concerned with policy-based RL, so there's no value function, there's no additional function approximation. And what is the sort of baseline result here? So there's this result called policy search by dynamic programming. So this algorithm is like over 20 years old. It's stated for this what is called a mu reset setting, which is a different interaction protocol. In this setting, the learner is given access to these H additional reset distributions, and with the sort of promise that these are a good exploratory distribution to start from. So you can sample from these, so you can do online rollouts from these reset distributions. And the sort of result that you have here is that under these two assumptions, so the first one is like a sort of coverage assumption called bounded concentrability. So if you're interested in the math, you can look at it, but like just you don't need to. The second one is a representational assumption on the policy class called policy completeness, which roughly says that like when we apply this like policy improvement operator, the resulting policy still lies in our class. Under these two assumptions, PSDP achieves this polynomial sample complexity. So for our work, like we wanted to understand like whether these two assumptions can be modified, relaxed. And since this is like a very classical algorithm and it has like a lot of citations, surprisingly we could not find any results that do this. So first of all, we have some bad news. So our first result is that if we remove access to this exploratory distribution and we only give the learner the promise that there exists some distribution, so this is an assumption called coverability. From this paper by Xie et al. Even here, even if you have access to a simulator from which you can query from any state, you cannot learn in a sample efficient way. The second lower bound we have is that if you do not make any assumptions on representation, you also cannot do anything. And this holds for the mu resets setting. Here there's like an open problem of whether you can do something if the policy class is realizable, and we don't actually know. We can show that PSDP as well as like this conservative policy iteration algorithm both fail. So we have lower bounds for these two like settings, And we can ask like, what happens if we like have a more powerful interaction protocol? So here we actually have a positive result. So our positive result holds for this block MDP setting, which is like a sort of canonical setting for RL when you have like very large state spaces, but there's like some sort of control on the complexity of the problem. So I'm not going to actually describe what the block MDP is. I think the next talk will. I'll just say that the previous two lower bounds that we proved were actually block MDPs. And here we can get a positive result, which it's polynomial in some sort of concentrability parameter, as well as S, which is like measures this intrinsic complexity of the block MDP. And I'd like to highlight that this is like fully agnostic. Like we don't make any assumptions about like having access to a decoder class or like any like other additional function approximation. And on a technical level, like we accomplish this by constructing this like carefully constructing this like sort of policy, what we call a policy emulator. It's like a smaller tabular MDP that allows us to evaluate all the policies in our class. And so the takeaway here is that if you have both the simulator and the mu resets, then you have sample efficient learning. And so that's it for my talk. And yeah, thanks.
We have loads of time for questions, if anyone had any.
Is there any hope of getting, right here? Hi. Is there any hope of getting some sort of Oracle efficient, like computationally efficient upper bounds in this setting?
Yeah, so our algorithm is very much not Oracle efficient. I think we required access, we thought about it a little bit. We require access to like a proper tabular planning oracle. So let's say you have some policy class, this oracle tells you like it returns to you the best policy in that class over a known MDP that you constructed. But in general, I don't think this is, it's not the same as like, like the oracle that PSDP requires, which is basically like a supervised learning oracle, right? So yeah, we did not think too hard about that, but yeah.
Are there any other questions? Yeah. If not, we can move on to the next speaker. Yeah, I guess. Yeah, talking of oracles, I guess. So Dhruv is going to give us a talk about necessary and sufficient oracles for RL. I'll take it away.
Thank you. So this is based on joint work with Dylan Foster. And somewhat similar to the previous talk, the main challenge we're going to be interested in here is the challenge of large environments. So many of the potential application domains for reinforcement learning involve environments with either massive or even infinite state spaces. Examples come from robotics, from language models, and from games, and from more. And in all of these domains, the commonality is that the classical model of a small and unstructured MDP and the classical algorithms that enumerate exhaustively over the MDP's state space are insufficient to get any good guarantees. And the central challenge here is to design efficient RL algorithms under weaker assumptions that enable us to work with extremely large state spaces. So in the theory literature, this is known as RL with function approximation. And in this talk, we're interested in understanding computational efficiency in this setting. Now there's a question mark here, which is how do we usefully quantify computational efficiency? And I will get to that in the next part of the talk. But first, let me zoom out and talk about modern machine learning. So in the past decade and a half, we've seen breakthroughs in problems ranging from image classification to interactive decision-making for games, to language modeling, and to image generation. And at first glance, all of these problems look quite different. But if you peek under the hood, you will see that reinforcement learning relies on something called value function estimation. Language modeling relies on next token prediction. Generative modeling relies on score estimation. all of these are supervised learning primitives. They are regression or classification problems where deep learning has proven to be extremely useful. So in empirics, there is this ansatz that supervised learning is often surprisingly easy on natural data, and more generally, that gradient descent tends to find good minimizers, maybe more often than we would expect. And this ansatz is sort of the backbone, or at least one backbone, of these recent successes in language modeling, in image generation, in RL, and in other domains such as imitation learning. But this is the empirical perspective. As theoreticians, how can we hope to exploit this ansatz? We can try to design algorithms that are oracle efficient. So we can say an algorithm is oracle efficient with respect to some oracle O if it is provably correct and computationally efficient modulo query access to the oracle. And so this gives us a way to design algorithms that essentially exploit the ansatz that this oracle should be heuristically implementable, and they let us circumvent worst-case computational lower bounds. So one classical example comes from online learning. So follow the perturbed leader is a reduction from online linear optimization over some decision set to offline linear optimization over the same decision set. And you can think of this as an algorithm that's using an offline linear optimization oracle. Why is this cool? It's cool because the reduction works for an essentially arbitrary decision set, whereas end-to-end computationally efficient algorithms for this online problem require stronger assumptions such as convexity. And so we've greatly broadened the scope of the sorts of problems that we can design principled algorithms for. A second family of examples comes from reinforcement learning. So there are many recent algorithms that reduce reinforcement learning with rich observations to a variety of optimization tasks. The benefit here is that these reductions now apply in settings where the state space is very, very high dimensional. Think of image data. Whereas if you wanted computationally efficient algorithms, almost all the algorithms we know for RL require the state space to be small. So this is the tabular MDP setting. But there is a catch here, which is that fundamentally, an oracle is an assumption. Because in the worst case, any of these useful oracles are computationally intractable to implement. This is not so bad in the online learning setting, because Kalai and Van Paula showed that the offline linear optimization problem is no harder than the online problem. And so in a provable sense, the oracle that they assumed to solve their online task was actually necessary for the problem they were trying to solve. But in reinforcement learning, the picture is much more murky. So there is a whole zoo of oracles that we have tried to use for RL with rich observations. There are value function estimation, there's inverse kinematics estimation, and there's min-max feature learning. And it's not really clear which of these are necessary and which of them may be more complex than necessary. So the question that this motivates is, what oracles do we actually need? And more generally, can we find some correspondence between the structural assumptions that we make about the reinforcement learning environment and the types of oracles that we need in order to design an oracle-efficient algorithm? So that's the question. Let me now talk about the setting and our formula results. So you're probably all familiar with episodic reinforcement learning from the last few talks. So the agent is interacting with the environment. In each episode, the environment passes some observation from some space X. The agent plays an action. The environment transitions to a new observation. This proceeds for some finite number of steps. That's one episode. The agent's goal is to interact with the environment over some number of episodes and eventually produce a good policy or set of policies. And I'll talk about what I mean good in the next slide. So I said that we want to understand MDPs with large state spaces. And perhaps the most commonly studied family of such MDPs is the family of block MDPs. So block MDPs are defined in terms of a concept class phi. And you should think of this as analogous to the concept class in pack learning. So in the RL setting, a concept class is a collection of maps from some observed state space X to some latent state space S. You can think of X as the space maybe of images, which is far too large to enumerate. And you can think of S maybe as some much lower dimensional space, for example, locations in some region. And this may be small enough to enumerate. And for a concept class phi, MDP, we say it is a phi decodable block MDP if the observed state space is X But somehow, for any observed state, little x, the transition data at that state only depends on a much more concise object, phi star of x, where phi star is some unknown concept in your concept class. So there's a concise representation of the MDP, but we do not a priori know how to decode to get to that concise representation, and that's where the challenge is. So this is the this is the structural assumption that we are assuming, and it is parameterized by this class phi. The task we want to solve is reward-free reinforcement learning. So here the goal is to find a policy cover, which is essentially just a set of policies that visit every latent state with a near maximal probability. So this is quantifying the notion of exploring the environment. Our first main result is the following. We can show that reward-free RL in phi decodable block MDPs for almost any concept class phi is polynomial time equivalent to a certain supervised learning task, which we call two-context regression for the concept class phi. And the interpretation here is that this supervised learning problem is a necessary and also sufficient oracle for this RL task. What does this task look like? It's a regression problem where we see two contexts and some real number. And we want to estimate the conditional expectation of the real number y given the context x1 and x2. And the assumption we make, the structural assumption, is that the conditional expectation only depends on x1 and x2 through phi star of x1 and phi star of x2. So why is this useful? This is a useful oracle for RL because it lets us do things like solve inverse kinematics. So if I give you some x1 and I give you some x2, which action was more likely to take me from x1 to x2 in the environment? It lets us do things like that. And what this result says is that RL is essentially computationally equivalent to being able to solve these sorts of problems. Our second result shows that if we give the agent additional access to the environment, so if we give it to the ability to reset to states it's previously seen, the problem becomes computationally strictly easier. And in particular, we can get away with a one-context regression oracle. So you should think of this as roughly equivalent to value function estimation. And our third result goes beyond block MDPs. So you might ask, in what generality do these sorts of reductions hold? Well, we show that in low-rank MDPs, which are the next more general family of large state space MDPs, we show that there is no analogous reduction to one-context regression, even when you have reset access. So the interpretation here is that low-rank MDPs are qualitatively harder than block MDPs. I would say the takeaway for all of these results is that oracles are a useful lens for quantifying the computational complexity of reinforcement learning. To conclude with some future directions, all of our results were for reward-free reinforcement learning, where you want to explore the environment. You might ask, what about reward-directed reinforcement learning? So this, I think, is a very interesting, maybe difficult question. Like, is this easier or is this similar in computational complexity? A second question is, when can we get away with regression-type oracles versus min-max oracles, which seem to be more efficient in some more general model classes? And the third, most general question is, can we develop a similar computational taxonomy in model classes more general than block MDPs? Thanks for listening.
We have some time for questions. Adam?
Wait, sorry, maybe this is covered in the future directions, but so for low-rank MDPs, is there a positive result for context regression? Because okay, I see, so we don't know.
Like, as far as I know, the min-max oracle in, I think, your paper is the best.
Okay, thanks.
Ayush?
Is there any other oracle except for inverse kinematics that uses, like, goes beyond one context that you know of in the setting?
Beyond one context? I mean, there's like things that look sort of similar. Like there's a bunch of variants of two-context regression, like in like the music paper and things like that.
But they're all of the flavor of inverse kinematics.
They're all the same flavor.
Yeah.
I guess this result kind of shows that you would expect that. But like the min-max is sort of the most powerful we know, but it also looks more nasty.
Right.
So that motivates like the second question here.
Mm-hmm. Great, thanks.
Let's thank the speaker again.
Okay, cool. Okay. Hello, everyone. So I'm going to present a joint work with Gerge, who's here with us, and Luca, who couldn't make it, unfortunately. And in the same vein, I'm going to talk about reinforcement learning with functional approximation, and more specifically, how to do exploration or efficient exploration in infinite horizon environments. So unlike the previous talks who focused on the finite horizon setting, which essentially aims at solving the optimal Bellman equations via like some form of backward deduction, in this talk, I'm only going to focus on like discounted environments in which I'm trying to solve like the optimal Bellman equations here, which are just given by like a fixed point equation in the value function, which is essentially just the expected discounted return. And surprisingly, if you're familiar with this literature, you'll see that the vast majority of the papers on functional approximation are all or almost all dealing with the finite horizon setting. And I think we have like a good understanding, or at least like over the last 6 years, we got a good understanding of how and when we can actually do efficient learning. But surprisingly, in the infinite horizon counterpart, like the situation is much more dire, and we don't even have like good results in the simplest structured settings. So this is what this presentation is about. And so just to set up like the interaction protocol, because we are doing discounted MDPs, once in a while the environment is going to reset over the course of the interactions, and whenever the environment resets to the initial state distribution, we're going to like define a new epoch in which we're going to like update our policy with new samples and so on and so forth. And the goal is very simple. We just want to get like a near optimal policy as fast as possible. And to quantify this, I'm just going to introduce like an intermediate measure. Oh, we don't see it actually. But I'm just going to look at the pseudo-regret, which is essentially just the sum of the suboptimality gaps of the policies that my algorithm computes. And just as a shortcut notations here, H is going to denote the effective horizon. And whenever I take mu of some policy, I'm referring to the state action occupancy measure of some policy, which just tells me like what fraction of the time my policy spends in a given state action pair. And I'm going to heavily rely on those notations. Okay. To enable efficient learning, we need like some assumption on the environment. And the one I'm going to consider here is that of a linear MDP, which just assumes that I have access to a known feature map phi, such that my transitions are going to be linear in phi of a given state action pair xa and some other vector depending on the next state. And the nice implications of this assumption is that this actually linearizes the conditional expectation operator of any value function defined on the state space. And so I'm going to use the notation PV for the conditional expectations of some function V. And what's nice with this is that we actually know how to estimate this kind of object. We can just collect samples, perform a linear regression to estimate this quantity, and I'm going to denote my transition estimated by pi hat of k. And this is simply just a linear regression over the history that you have. And because I'm doing like optimistic exploration in the next slides, just to flash the way the kind of bonuses that we're going to use, it's fairly standard. I'm just going to use like elliptical bonuses, which is like the reweighted norm of the features in a given state action pair, where like the lambda here is an empirical covariance matrix. And so if you were to approach this problem very naively, like the first idea that you could try is essentially to just run optimistic value iteration. So you replace your transitions with your estimates, you add your bonuses, which act as an estimate of the uncertainty on your estimates pi hat k vk. So you really want the upper bound here to hold for every state action pair, and then you're just going to iterate and hope that it converges. But because we're doing RL with functional approximation, those estimates, and as those estimates are computed like via linear regression, this pi k hat here does not induce a valid probability distribution. And so like there are a bunch of properties that break down. And essentially the short consequences, like the short answer is that this algorithm alone is not going to converge to anything. So we need to do something else on top of that. And essentially the algorithm that I want to present is just two simple modifications away from that. Something to note here is that I'm truncating my Q estimate by like h, which is the effective horizon. And this is actually going to be necessary in some way to prevent like an exponential growth of my iterates. And I'll come back to that later. But so the first modification that we can apply to avoid relying on some contractivity property or some monotonicity, is simply to replace the greedy update by regularized policy update. So I'm just going to run mirror descent, and my new policy is just going to be a softmax of the new Q iterates regularized by the previous policies. And so this is nice because now you can actually get a bit further than before. But there's still one key issue. And the issue is that in linear MDPs, so first, if you unroll this update, what you're going to get is just an exponential of the sum of your Q iterates, if you just unroll the whole thing. But it turns out that when it comes to linear MDPs, the way the bonus is defined is essentially this elliptical bonus weighted by the log covering number of some function class that is known to contain all your iterates. And so what this means is that the constant that appears here is essentially the number of parameters you need to represent sum of Q iterates. But because in this case we're talking about truncated linear functions, essentially, you're going to need d squared times k parameters, and so you're going to get like a vacuous regret bound. So this breaks down. So the second idea that we need to introduce here is that I already said we cannot remove the truncation, otherwise the iterates are going to blow up. But like maybe we could try to implement some like soft truncation, and that will hold like locally. So what if I just replace that function, and I just multiply my dynamic programming update with 1 minus some function pi k plus, which is going to map any state action pair to the interval 0, 1, plus the effective horizon times this probability. Now it turns out that if you squint at it a bit, you can rewrite this algorithm and notice that this is exactly equivalent to running optimistic value iteration in another Markov decision process in which you added like an artificial sync state to which you can transition with these probabilities. And this sync state would give you like maximal return. And so for the spatial choice, when those probabilities are essentially just the sigmoid of the bonus, it's effectively going to act as a hard truncation. Because whenever you visit underexplored states, the bonuses are going to blow up, so the sigmoid will be close to 1, and so the update is going to essentially clip this away. And so the nice properties that this gives us is that now the nonlinearity is removed, so the covering number is down to essentially d squared. So we can apply the analysis of optimistic regularized value iteration, and this is going to work. But like very briefly, the way it works down is that once you observed that you're running value iteration in a different MDP, you're just going to try and relate the regret you care about to the regret in this new MDP. And then so we know that we can control this. And the question is how big the remaining terms are. And so it turns out that for the original regret, you're just going to get like some square root of k terms, which we know how to handle. So like this is just the sum of the bonuses along the agent's trajectory. So this is like a standard quantity we can control with like an elliptical potential lemma. This is just an optimization error. And the remaining term, which is the cost you have to pay to make this translation, is only going to be logarithmic in the number of epochs. So essentially, you're not paying anything for doing that. And yet, you still get a square root of k regret in this kind of environment. And I forgot to mention that this is done in polynomial time, so the algorithm is obviously efficient. And just to flash the second result we have, you can also just plug this result into a standard decomposition in interactive imitation learning and get optimal rates as well. And I don't know if I'm good on time or not. Yeah. So just to conclude briefly, like all you need to do to achieve like efficient learning in in discounted linear MDPs is simply to apply those two modifications to value iteration, which is to use like softmax policies and soft truncations. And just to conclude on some like related questions, obviously, it would be great to like extend it to the average reward setting, but so far we haven't really managed to do that. You could try to think about more general structural assumptions, such as linear occupier realizability that Zach is going to talk about just after. And yeah, we don't see that, but I'm also thinking about whether we could come up with a better notion of misspecification, because what we have right now in linear MDPs is kind of meaningless. But if we look at the analog of the linear MDP assumption in causal inference, there we actually know how and when misspecification is harmful. So I'm wondering if there is like something we could do in error as well. And I'm happy to take questions. Thank you.
Yeah, thanks for the talk. Are there any questions? So can you say a little bit more about...
Is there...
Oh, there is.
Can you say a little bit about how the softmax policies allow you to avoid this contraction?
Yes. So, okay, so I don't have it on the slide, but essentially when you're trying to upper bound the regret here, what you would end up with typically in like those analyses is that you would end up with the sum of the bonuses, so that's fine, and you would end up with another term, which is a sum of the successive differences of your Q iterates in expectation under the current policy. And so the way this is typically small is that if you have contraction, then successive iterates are going to be close to each other. And if you have monotonicity, it's going to be a negative completely. But because we cannot do that, you could like reindex the sum to look at a difference not in terms of Q values, but in terms of occupancies. And the way to make occupancies close to each other is just by regularizing. So that's how you get this.
Let's thank the speaker again. Yeah, Priyank from Columbia.
Yeah, it's fine.
No, it's okay.
So I'm going to talk about Q-learning and special work. It's with my advisor, Shipra Agrawal, who's also at Columbia University. So specifically, we design a Q-learning-like algorithm for both average reward and episodic settings in RL, which are really popular. We have seen previous talks talking about both these settings already. Hopefully, it's not too much of a big deal on describing these settings. So the model is about online reinforcement learning, where there's environment, agent, the transitions and reward distributions are unknown, so it's a learning setting. And the transitions rewards follow Markovian assumption, and specifically we assume throughout the talk and the paper, the state space and the action space is finite, so it's a tabular setting of RL. And the two settings of concern are episodic. In episodic setting, the agents interact with the environment in repeated bouts or episodes of fixed and known duration, and the environment is assumed to reset after each episode. And in average reward reinforcement learning, the agents interact with a single trajectory with no resetting of the environment. Until now, what we have observed that there have been different techniques which deal with both these settings, and this is the kind of first work which tries to combine and give a single algorithm which works for both settings. If you think of some examples of reinforcement learning, so for example, in task learning, let's say game playing, robotics, or online shopping, the idea is their interaction is repeated episodes, but the episodes are of uncertain length, and the length of the episodes indeed depends on the strategy used by the algorithm. And the typical aim is to learn a stationary policy. And a common practice is to apply episodic RL in these examples. And in episodic RL, if you recall, the duration of episode is fixed and known. So as a result, the algorithm ends up learning a non-stationary policy. Even the optimal policy is non-stationary. That defeats the basic understanding in these settings where sometimes the optimal policy only depends on the state. It doesn't depend on the time the agent is from the end of the episode. Similarly, in long-term decision-making tasks, for example, inventory management, queuing, there is a single thread of experience, but there are certain states or certain good states like empty queue, full queue, out of stock, or full inventory, which are visited often under reasonable policies. And by domain knowledge, we know the optimal policy lies within these reasonable set of policies. And one can even argue that the previous tasks I showed can also be thought of a long-term interaction. So there's a need to have a fluid description of both these settings, an algorithm that cover both these settings together. And this is the motivation of our work. And the way we do it, we make a key assumption, which we call it frequent state assumption. And the assumption goes like this. There is a frequent state S0, such that under any policy, under any starting state distribution, the expected time to visit S0 is bounded by H, which is known. So this will capture a certain class of average reward setting, but more importantly, it captures the episodic setting, and it captures indeed a more generalized version of episodic setting, where the duration of episode may not be the same all the time, and this S0 becomes naturally the end of state episode, or the starting state of that episode. As a performance measure in our work, we capture through regret. And the main result is high probability regret bound, which scales as h raised to the power 5 s root at, where s is the size of state space, a is the size of the action space, and dependence on h is out of 5. And as a corollary, we can get a similar bound for episodic setting. Key points of our results are we have a single Q-learning-like algorithm which works for both these settings. Indeed, say the algorithm does not need to know what environment it's working on. It is going to work fine. And at the heart of our results, we develop a novel Bellman type operator under span semi-norm. Under this frequent state assumption, we can show that it's a contraction. So one can think that this kind of assumption is quite strong. Well, indeed, it's strong. But I argue that this assumption is not as strong as contemporary assumptions made in literature in model-free reinforcement learning, especially in case of average reward setting. So previous works have made even more restricted assumptions where all the states are recurrent and the worst case hitting time is bounded, which means that if you deploy any stationary policy, it's going to induce a stationary distribution in a small number of steps, and that stationary distribution would be such that all the states are visited frequently often. In comparison, we make a more benign assumption. Specifically, we only need to have one state to be recurrent. And we don't need to know the identity of the state. The algorithm doesn't depend on that identity of that particular state as 0. There are some works which make lesser assumption average for setting in model-free style of algorithm, but the algorithms might be a little more complicated than just vanilla Q-learning. So what's the key idea? The key technical idea is to look at Q-learning algorithm as value iteration implemented using samples. So let's recall what's value iteration. If we knew the transitions and reward distribution, value iteration is a very popular and very simple procedure where one can calculate the optimal value function, where I'm representing here as V. And once we knew the value function, and if we knew the reward distribution, it's easy to get the optimal policy. So in some sense, it's instructive to think of value iteration as trying to find the fixed point of the operator L, or the optimal Bellman operator. And it converges when L is a contraction under a suitable norm. So it's known that in discounted setting, there is a very natural way of contraction, seeing as a contraction. In episodic setting, it's easy to see we don't really need a contraction property to have learning or convergence. However, in average reward setting, we need additional assumption. And our main technical contribution is to propose a new operator. For lack of more creativity, let's call it L overline, which is a contraction under span semi-norm under the frequent state assumption. And this L overline is nothing but averaged application of the L operators. So L overline V is just averaged application of L, L square, L cube, so on till the H index. So in essence, what we are suggesting is a new version of value iteration but instead of using the L, finding the fixed point of the L operator, just find the fixed point of L over line. And how do we think when the transitions and rewards are unknown? So recall the Q-learning in its natural form gives such a simple answer. So Q-learning, just a one-line introduction, is an algorithm which is trying to estimate the optimal Q function by delicately balancing the learning rates. And if you use well-calculated exploration bonuses, one can sort of view that this Q-learning algorithm is implementing the L operations repeatedly in a sample-based asynchronous format. And our tree algorithmic contribution is to look at Q-learning and modify it slightly so as to it starts estimating optimistically the L over line operations. So effectively, we implement L over line square, so on and so forth. So to summarize, the two technical ideas are to show that L over line operator is indeed a contraction of the frequent state assumption under span semi-norm, and to design the Q-learning algorithm such that we can control the sampling error while we calculate these operations. And the key takeaway from this paper is that we have a same algorithm, Q-learning, which achieves root T regret bound in both episodic and average reward setting. And this result really makes sense for practical scenarios where H is small or known. And I hope that the frequent state assumption, the contraction properties, is general and could be of independent interest. Thank you for listening.
Thanks for the talk. Are there any questions? Yeah, I had a quick question. So the frequent state assumption that you made, is that a minimal assumption under which this operator is contractive?
Not really. So there are versions of this frequent assumption we can make, and we can have the bounds, and those versions would be strictly weaker. But effectively, it would look like this.
But your result is like, whenever it's contractive, your algorithm works, right?
Say that again.
Whenever this operator is contractive, your algorithm works, right?
Yes.
Oh, okay. Oh, thanks.
Thank you.
Are there any other questions?
Thank you for the talk. So you need to know this bound H to define the operator
Yes.
in the first place.
Yes.
Did you investigate how sensitive it is to maybe too large H or too small H? Did you investigate that?
Yes, I agree that we need to know the edge. Currently, we don't really know how we can estimate this edge, but there are some practical examples where the edge is naturally defined. For example, if you are in a situation where the queue can be full in some fixed number of steps or higher, there's upper limit of number of steps where queue can be full, there will be no edge is defined. But in general, we don't know. And the regret bounds, as far as we understand, would scale with H. Like if H is really large, regret bounds can be worse.
Okay, thank you.
I'm sorry, yeah, can we hold off other questions for offline? I apologize.
I'm happy to take questions offline. Thank you.
Yeah, next we'll have Victor giving us a talk about average reward MDPs.
All right. Hello, everyone. So I'm Victor, and I'll be presenting a work I did with my PhD advisor, Bruno, in the room somewhere. So I would like to talk today about a new problem, new insights in actually quite an old learning problem, that is regret minimization. in Markov decision processes. And perhaps the main takeaway from my talk and perhaps the destination is this figure here. When I plot the regret over time of standard algorithm, plural standard algorithms, and our version, our algorithm, which is a small patch of the standard. So I will start by describing my problem better so that we can understand this figure better soon. So Markov decision processes, set of states, state of actions that I like to bundle together as a pair space that I denote Z, a transition kernel, and a reward function. And what is important is the laws of the dynamic that are defined here. That is, at time t, you observe a state big S of t, and you play some action big A of t, and then you get a new state generating according to the transition kernel, and a reward generating according to the reward function. And your goal is to choose actions in order to gather as much reward as you can over time. So on a small note here, there is no discount, and big T here is actually going to infinity, so it's infinite horizon. And I'm looking at the learning version of this problem, where you don't know the transition kernel nor the reward function, and you still want to gather as much reward as you can. So this problem, usually we don't say we want to gather as much reward as you can. We say it in an equivalent way. We say we want to minimize the regret, because we compare our learning performance to what an optimal planner can do when you know everything in advance. Because when you know everything in advance, you compute the optimal policy. And this optimal policy scores a per step average reward of G star, called the optimal gain of your MDP. And over T steps, this optimal policy scores T times G star. And you compare to that. All right. So many algorithms that have very nice regret guarantees, but the one with the best regret guarantees in theory so far are optimistic model-based algorithms. So two words, model-based and optimistic. Model-based because it's about constructing confidence region, maintaining a model for the underlying Markov decision process. It's a set of Markov decision processes that are plausible under current observations. And optimism is about the way you pick a policy, you pick a strategy from this confidence region. The way you do that is you estimate the score of every policy optimistically. The score is the asymptotic average amount of reward that you get with that choice of policy, and optimistic because you look at that score for every plausible Markov decision process, and you take the maximum. Okay. So this is the optimistic score, optimistic value of a policy, and the optimistic policy, or optimistically optimal policy, is the policy that maximizes the optimistic score. And in the end, this family of algorithms look like this. You have episodes. At the beginning of an episode, you pick a policy. You compute your confidence region. You pick the optimistic policy, and you play it over and over until some criterion is met that says you should stop and change policy because it's too old. And most of the literature says, oh, you should be very careful at the choice of confidence region because the better the confidence region, the better the regret. And we say maybe people disregarded the choice of the way episodes are managed. They all do the same, but we say maybe they all do the same, but wrong. Okay, and this is what we see on this picture. On the left, it's a classical learning algorithm. And on the right, it's a small patch that we add to it. So what we see is that the regret is no, I have no, is there a laser on this? No. The regret is flat from time to time, most of the time, actually, because it does not grow. Amazing, thank you. Well, it does not grow because the current policy, the optimistic policy, is optimal. It's the best policy. And on the red stripes, the regret grows because the current policy, the optimistic policy, is not optimal. So we see that there are, so we call this bad episodes and good episodes, okay? So we can see that there are few bad episodes, but on the left figure, they seem to grow in size, and actually they do. And under our patch, you have much more episodes, bad episodes, but they are much smaller. So that overall, you cannot say that one algorithm has better regret than the other. Okay? And to quantify the smoothness of the regrets, we introduce, it's not really a learning metric, it's more of a learning quantifying the behavior of algorithms that we call the regret of exploration. Is the regret not starting from t equal 1, but starting from t equal a bad episode, the beginning of a bad episode that is advanced in the learning process. Okay, and you can show that fairly easily that for standard algorithms, this quantity grows linearly with t. This is skip, and it's pretty easy to see why, because they use all use a variant of a doubling trick to manage episodes. And the doubling trick says you run your policy, your current policy, until the visit count of some state action pair doubles, and then you change your policy. It means that you wait that the amount of information doubles somewhere in your big Markov decision process. And obviously, if you wait for it to double, bad episodes will explode in duration. And you say, no, you should wait for a multiplicative increase. Multiplicative by f of t. And f of t, if it's not too big and not too small, you're happy. Why? Because you have the exact same regret guarantees, but much better regret of exploration. You drop from linear to a big O of log t. And you have other advantages, like the regret is more stable overall, small variance, and this kind of properties that are pretty nice to have. So I've said, to take a bit of distance, long bad episodes are bad, and to have shorter bad episodes make episodes shorter. So you can say, yeah, it sounds like an obvious result. Actually, it's not, because I'm not talking about episode, but about a local regret, localized in time. Because you can stop a bad episode just to begin a new bad episode, and another episode with the optimistic policy being not optimal. So why is it that we don't use suboptimal policy many times in a row? And it has to do with quite interesting behavior of the constant region over time. Because if you take an algorithm that has a nice regret, that has nice regret guarantees, you can show that there are two kinds of state action pairs, the good and the bad. The good are visited linearly many times, and the bad are visited at most logarithmically many times. And the constant region attached for these state action pairs will behave very differently over time. So if you take the constant region for a reward, so it's an interval, we get it with Azuma FD. And for the good state action pairs, big N here is about T. And this means that when you're going to visit this state action pair again, the width is going to decrease, but it's going to decrease slower than the center, the empirical estimate, moves, meaning that the constant region is shaking around. Meanwhile, if you have a bad state action pair, it's the opposite. The width decreases faster than the center moves, so there's a global shrinking behavior. So I just finished this is the slide. And you can explain why the regret of exploration is small with this kind of property. It's because if you use a bad policy, you have a constant region of a bad state action pair that is too big. But with this kind of property, you're going to iterate the policy. You're going to play that bad state action pair. So the constant region will shrink at a quantifiable speed. So the optimistic value of that policy will decrease fast enough so that it's not optimistically optimal anymore. And so if you update your episode soon enough, you will reject the policy and switch back to the optimal one. And that's it for me.
We have time for one quick question, which Max has apparently.
So I think it's well known that one can get non-asymptotic logarithmic gap-dependent regret from optimistic algorithms. There's a 2019 paper of mine that shows this. I'm kind of curious, sort of, what is being added. What is sort of like, is it the infinite? What is like the new technical difficulty? Is it the infinite horizon setting that's kind of making things quite more difficult, or the average reward setting?
Are you concerned about the big wall of log T here? That is.
Yeah, the question is that I think there have been quite a few results that have studied sort of the O log T results. There's also some work from Tengi Ma's group, from Simon Du's group, that understand that this is happening in the sort of optimistic algorithm space. And I'm kind of curious, sort of, what is the new technical challenge that's being addressed?
Well, first, this is an asymptotic quantity, okay? And the algorithm that you see here, it's a standard optimistic algorithm. And the big O of log T that you see here has nothing to do with the standard regret, okay? It's not that, I do not say that the regret is big O of log T. I say that this quantity, which is a limb soup, okay, it's basically, you see these red stripes? They are bound like at 100,000. It's bounded by log of 100,000, right? Because the regret is bounded by a log of 100,000, and I plot the regret. So the length of the red stripes is bounded by log of 100,000. But I think that these red stripes, will keep getting bigger and bigger. And this is what we quantify with this. Okay. So you have regret be big O of log T, but regret of expression being omega of T. It's not the same T. Did I answer your question correctly? Okay.
Cool. Let's thank the speaker again. For the final speaker, we have Zach, who's setting up. We apologize for the technical difficulties. Yeah, we have Zach.
Thanks everyone for sticking around. So first of all, I want to say that even though this is a theory paper, it is part of a larger effort to try to bridge the gap between RL theory and practice. So if you look on the practical side, like the algorithms that people typically use tend to be simple algorithms like PPO that are very practical and easy to implement. But they do lack theoretical guarantees, and actually they can provably fail whenever the task requires more systematic exploration. And then on the other hand, you have theory algorithms that are good on paper, and actually they can have sample complexity that can be exponentially better than their practical counterparts, but they tend to be computationally inefficient, or they make some unrealistic assumption about the environment. And actually this reflects a current gap in our understanding of when can we have computationally efficient RL. So it is fair to say that we are pretty far from having a characterization of what conditions on the environment or the MDP that are needed to enable this sample and computationally efficient RL. So actually very few end-to-end computationally efficient algorithms exist beyond the very simple tabular and linear MDPs. And so in this paper, we try to go beyond these simple settings by considering a natural generalization of a linear MDP. And we consider a setting called linearly realizable MDP, where we assume that the state action value function is linear in some given feature map. So this feature map phi is given to the algorithm, and you assume that qpi is linear in this feature, where qpi is simply the expected sum of future returns. And so as I said, linear realizable MDPs are generalization of linear MDP, but unlike linear MDP, where you assume something about the transition dynamics, so here we don't make any explicit assumption on the dynamics. So it's much more general in that sense. But despite the simple formulation of this problem, it is significantly harder than linear MDPs. And so the question we're trying to answer in this work is there a sample and computationally efficient algorithms for this setting? And so by that I mean, we want an online RL algorithm that outputs some policy pi hat, that with high probability pi hat is going to be epsilon suboptimal. And we want an algorithm that does this with a polynomial number of episodes and a polynomial computational cost. And so maybe a slightly less ambitious question is to ask for polynomial number of calls to some oracle that's used in ML. And so here I mentioned online. So online here refers to the type of access that the algorithm has, the access to the environment. So in online access, the algorithm can execute action and observe rewards and generate trajectories. I also want to mention another type of access that I'm going to mention in this talk, which is local access. So this is the same as online access, but the agent has the extra ability to reset the state to any previously visited states. So for the algorithm of this paper, we're going to be focusing on the online access setting. So before I show you some results, I wanted to mention a couple of related MDP assumptions that are also generalized in linear MDP and where we know, where we have a better characterization of what we can do. So you have linear Q star. This is where the optimal state action value function is linear in some feature map. We know that this is intractable in online setting, but it becomes tractable if you assume some value function gap and local access. Then you have linear Q star V star, where you make the additional assumption that the optimal value function is linear. We know that this is statistically tractable, but not computationally tractable. And then you also have linear Bellman complete, where the Bellman backup of any linear function of phi is also linear. And here, if you're happy to pay an exponentially in actions, then there's an efficient algorithm by Noah. So what about this qpi realizable MDPs? So here's what we know. If you have local access, then there's an end-to-end computationally efficient algorithm. In the online access, there is a sample efficient algorithm, but it is based on this notion of global optimism, and it's not computationally efficient. And in general, like we don't know of any computationally or oracle efficient algorithm for this setting. And so this is where this is the main result of the paper, is that we have a sample and oracle efficient algorithm. So more specifically, we have an algorithm that outputs a policy pi hat, such that pi hat is epsilon optimal with high probability. And we have a sample complexity that is independent of the size of the state space, because the state space can be infinite in this case. And the algorithm makes a polynomial number of calls to a classification oracle that I'm going to describe in the next slide. So one thing to note here is that if we are aiming for suboptimality epsilon, the sample complexity depends on polynomial union 1 over epsilon, and the number of oracle calls actually is independent of epsilon, which is nice. So the oracle in question is an oracle that takes in a sequence of triplets of costs, states, and actions, and returns the policy that maximizes this weighted classification objective. over a set of policies that we construct explicitly as a function of phi. So I don't have enough time to go over the definition of this pi, but the things that are important to note here is that if you are in constant dimension, then you can implement this oracle efficiently. So in other words, if you're happy to pay exponentially in dimension, then this oracle can be implemented efficiently. But in general, if you're not in constant dimension, then this is NP hard. But again, like this oracle is standard, and it's often used in practice. And it can even be reduced to binary classification. Also, oracle efficiency is non-trivial because it is known that there are some RL algorithms that are simply incompatible with oracle efficient implementation. And such algorithms typically are based on this notion of global optimism. And the only other sample efficient algorithm for this setting is also based on global optimism. Okay, so quickly, I wanted to mention something about the algorithm without going into details. So other than the fact that it's sample and oracle efficient, the algorithm template is useful more broadly, so beyond this linear realizable setting. And the template here is a combination of dynamic programming for learning the value function combined with a specific and explicit test for distribution shifts. And this template has actually been useful because it generalizes this earlier algorithm called MTSS in the local access setting and enables to remove its recursion and simplifies the analysis as well. And it has also inspired this efficient RL algorithms in the context of language modeling, which Dhruv is going to talk about, I think, on Thursday. And okay, so without going into too much details, I just wanted to give you a very high-level idea of the solution approach. So it turns out that after all, these linear QPy realizable MDPs are almost like linear MDPs if you can essentially ignore certain low range states. So what I mean by low range is, so the range of a state X is essentially the maximum difference in Q functions for two actions A and A prime as you vary pi. So you look at the worst case over pi of this value function difference. So if you are given this range for any given state, then you could essentially just apply any algorithm for linear MDPs, and whenever you encounter a low-range state, you just play a random action. So by low-range states, I just mean that the range is less than some threshold epsilon. But in practice, we don't have access to this quantity because, well, this requires a supremum over policies, and it's complicated. But what the algorithm actually does is try to estimate it up to some multiplicative factor, and things go through. So the rest of the algorithm is similar to PSTP. So some limitations, obviously, are, well, we still lack an end-to-end computationally efficient algorithm, and there's an extra poly A dependence compared to the previous sample efficient algorithm. And we don't have any lower bounds. So it would be nice to have some lower bounds to also be similar to these other settings like linear Q star and so on. And with this, I can take any questions.
We're essentially at the end of our time, but we have maybe time for one quick question, and maybe we can take the rest of them offline. But one quick question. Okay, Adam?
What's the polynomial on epsilon? Is it the optimal, like 1 over epsilon squared, or is it worse than that?
Maybe epsilon to the 4 or something. I'm not sure, but I forgot. I think so.
Okay.
So I really liked how you opened the talk with sort of trying to close the gap between practical RL algorithms and some of the ones that you thought about. I have one just kind of very broad question. So oftentimes in RL theory, we like to think about static supervised learning oracles, but in practical RL implementations, we're doing things incredibly asynchronously. So for example, we're never actually fitting a policy loss or fitting a Q function loss to a completion. We're always taking these like small gradient steps, and we find that things tend to collapse if we do that. How would you think about kind of moving the theory towards something that kind of reflects the kind of inherently asynchronous nature of RL algorithms that we see in practice?
So you're saying that in practice you do things with value functions instead of like,
No, what I'm saying is in practice you never actually solve the supervised learning oracle problem to completion. And if you do that, then things tend to collapse quite catastrophically.
Right.
So how do you sort of think about like kind of charting a way towards understanding maybe some of the more optimization considerations that we encounter?
I mean, the results of this paper are still kind of like still far removed from those practical considerations, but it is sort of trying to broaden, the set of settings that we can say something about. But
cool, that makes sense.
Let's thank Zach again. And yeah, thanks again for all the speakers, and thanks for attending. Hey, what's up? How are you, dude?
Good. Amazing.
Unusually annoying.
C'est un laser de catégorie 2. Ouais, voilà.
I don't work in RL, but I really enjoyed your talk. At least, like, you give a really nice high-level story that I could understand.
Récupère là.